Hi folks, I'm going to do three things in this first video. One is I want to give a quick example of a center of gravity, or sometimes called centroid calculation, just because went over that really quickly on Tuesday, and I think you need to see an example. Um, then we're going to do also a fairly brief treatment on section 16.7, which is about generically how to deal with changing coordinate systems. We're going to see that the things like the rho squared sine phi when we were in spherical coordinates, or the extra r that came in when it was rd theta when we were in polar coordinates, those factors that sort of adjust the way the integrals work are a common feature, and it happens anytime you change coordinate systems. So we'll cover that, although quite briefly. Honestly, that's a quick thing. But it's kind of important because we'll need it later as we finish the section in Stokes's theorem when we're doing true vector calculus, which is coming this next week. And then finally, I'm going to start us in chapter 17, just a quick intro to vector fields and how that looks. Although we've seen them. We've seen vector fields in the form of gradients, for instance. All right, so let's get started with the example of something from a moment calculation. So I have a picture of an upper half plane semicircle, I guess I would call that. It's a y is positive, or y 0 to 1, I suppose, and inside the just draw it. It's the region bounded by the x-axis by the curve. It's the arc of the half of the circle, and so it's all this stuff in here. It's fairly common with these. I'm not showing you the thing I was drawing. Sorry about that. It's it's fairly common with these things that there's some symmetries that you can use to settle some issues. For instance, I can tell you that the center of gravity of this thing is probably about here. There's a special symbol people make for the center of gravity, which is a little hard to reproduce, but here, I'll draw it bigger so you can see what it looks like. It's like a thing called a reticle, but it's got two of the four little sections of the circle shaded like that. So that's a tiny reticle thing there. Anyway, that's the symbol for CG. This guy's got a y coordinate, which we would call y bar. And of course, it's got an x bar, but the x coordinate is 0. Right? And why is the x coordinate 0? Well, that's because of the symmetry of the object. It's totally symmetrical across the y-axis. So the tendency to rotate around the y-axis is, well, there isn't any. It's equally balanced on both sides. Did I mention the density of this plate? The density of this one is going to be 1, just so we get an easy example to get started with. By the way, the center of gravity or center of mass, when density is a constant, you might as well take that constant to be 1, because if it's a constant, it can be pulled out of both of the integrals we use to calculate the x bar and y bar, and so they cancel. So anyway, when it's really just something that has to do with the shape, the area of the shape, density is fixed, then this point has another name. They call it the centroid. All right, so can we actually calculate what y bar is? First, let me just say, if you figure out the total mass of this object and you times that by y bar, that ought to give you the same result as if you added up the things by doing a double integral. That should give you the same thing as what we call the moment around x. Do notice that the variables are opposite one another. We're thinking about the y coordinate of the center of mass, or the centroid here, but that those y numbers are how far you are from the x-axis. So that's the moment about x, and the moment about x is defined as a double integral over your region of the y-coordinate of a point times the density, which I said was going to be 1, times differential area. Now, the particular region I'm working with, I can set this up as an integral in Cartesian coordinates. So I would have m sub x equals an integral. It would go from -1 to 1 in the x direction, and in the y direction, it would go from 0 to the square root of 1 minus x squared. And then we would have y, and let's see, I said this, so this would be dy then dx, right, for the area. And that's kind of a hard integral to do. Well, let's see, maybe it's not so bad. Because when I integrate with respect to y, the antiderivative is going to be y squared over 2. And we'll evaluate that between 0 and this radical. And I think that's going to be okay because the y squared is going to take off the radical and we'll just end up with 1 minus x squared over 2. Yeah, that's kind of nice. And the bottom at 0, you get 0. So the final integral will be easier. I'm writing off the screen. It's been a little while since I've done these online videos. Sorry about that. Anyway, can we do one more version of that? I want to get this integrand simplified as much as possible before I go into it. Yeah, that's going to be 1/2 can come all the way out front. 1 minus x squared dx. I'm running out of space on this sheet of paper, so I'm going to have to start fresh. Let's see, we had, let me just recopy what was on the end of the last sheet. Integral -1 to 1 of 1 minus x squared dx. So the antiderivative is x minus x cubed over 3. Evaluated there to there, and also with that 1/2, I tend to forget my constants once I pull them out, so you guys have caught me on that a few times. All right, so upper limit, we get 1 minus 1/3, or that's 2/3. Lower limit, that's tougher to get, -1 minus -1/3. I think that's negative. So it becomes positive 2/3. We're subtracting a negative number, yeah. Oh, I should have done that in a quicker, easier way, which is to say, this isn't, both of the things being integrated or being evaluated are odd functions. So like the x, it becomes 1 minus -1 when we do that. So you get 1 plus 1 or 2. But the upshot is that you can just when you have symmetrical endpoints like this for the endpoint for the calculation, and you've got odd antiderivatives in there, you can just double. I feel like I said that really poorly. Anyway, what do we got here? 2/3 plus 2/3, that's 4/3, and divided by 2. I think the final answer is 2/3. Well, I don't believe that. I think something that had to have gone wrong in this calculation. Because I'm expecting a number between 0 and 1, sure, but I think it should have been something a lot closer to 0 than to 1. Oh, wait a second. We've got one more thing to do. What we just did was, which come back to where we started this, was the m sub x. If I'm looking to get y bar, I have to divide both sides of this by m, by the actual mass of the plate. And fortunately, that mass is rather quick to figure out because it's a semicircle, right? And we said its density was 1. So I might as well be talking about the area of a semicircle, and that's pi over 2. Right? The full circle has area pi, pi r squared if you want to get technical, but the r is 1 on this one. So yeah, pi, half of that is pi over 2. So finally, our y bar is our moment about x divided by the total mass of the thing, which is, we just figured out, 2/3 divided by pi over 2. That's going to make it a little smaller, a little more reasonable. Just pulling up something to use as a calculator. What do I just have? 2 divided by 3. And then that whole thing divided by, oh, I don't know how to do that in Desmos. Think of it. Kind of want to select, if I was on, okay, I can do it on my computer instead. Hold on. Let's go over to here. Desmos. Okay. So now I want 2 divided by 3 first, and then we're dividing that by pi over 2. Okay, better, right? It ends up with something that's less than 1/2. I was expecting it to be closer to the x-axis than to the upper boundary of the circle. And was I? Yeah, you were seeing that. Okay. So let's see. That's what we wanted to do first, is just show you an example of a moment calculation. And the real reason to do the moments is so you can figure out the x bar and y bar coordinates. That one is fairly simple, maybe a little too simple since I had a constant density, but usually adding in the density thing doesn't cause too much of an issue. So the other thing we need to talk about is the Jacobian determinant and how the change of coordinates stuff happens in multivariables. So I'm going to show you something out of the textbook now. This is the very beginning of section 16.7, where we're talking about just recapping what goes on in Calc 1 when we do a change of variables. So the U substitution stuff is what people call it. This is just changing really what we think of as the coordinate system. The original problem here is given as square root of 2x plus 1 times 2 integrated from 0 to 1 with respect to x. And what's the U substitution here? Though it's given in the paragraph right before this stuff. U is 2x plus 1. That makes sense. Put everything that's under the radical and call that U. Then you have to, I'm sure you recall doing this, you have to figure out now what is du, which is twice dx. And so this thing is almost perfect. The 2 up front and the dx in the back together make us the du. And the square root of 2x plus 1 now is just square root of u. The limits got changed from 1 to 3, whereas they were 0 to 1. And that's just gotten from using the transformation that x is being converted into u by doubling and then adding 1. So when we're at 0 and we double and add 1, we get 1. And when we're at 1, when we double and add 1, we get 3. So the limits on u are 1 to 3. Now, you should think of this as just the one-dimensional example of a generic thing, which is we're changing from one coordinate system to another where the problem becomes more convenient. So what the sort of gist of changing variables, doing a U substitution is that two distinct areas are actually the same thing. Y is 2 times the square root of 2x plus 1 is that arc, and the area under that between 0 and 1 is the exact same thing as this area. there's a factor, though, that contributes to sort of how we do things. See, um, area in the x space, the y and x coordinate system, and area in the y and u coordinate system aren't the same, but they are related. And the relation is, how did we change dx into du? We needed the du is 2dx. That 2 is the factor by which our differential widths correspond to one another. And it's really obvious in this picture. In the xy system, the area of the region we're talking about is between 0 and 1. But the region in the yu system is between 1 and 3. It's twice as long. That's the change. So what I want to do really is jump to a more general case of this, not concentrate on 1D. What we're looking at is a transformation. We're taking u and v coordinates. We had before it was just u and x. Now it's u and v. We'll turn those into x's and y's. So we've got 2 coordinates on the uv space. We'll get 2 coordinates in the xy space. Both of these you should think about as z can be plotted above those planes. So you're talking about volume of something under a surface in both cases. But the way area works in the xy space is dx dy. That's what dA is. The way area works in the uv space, well, it depends on what these particular functions are. They're calling them g. Sorry, I can't seem to highlight it. G there. And it wants to highlight the whole thing. Oh, well, I'm pointing at it. G and H, right? So what's happening there geometrically? You'll have a region in the UV plane, and when you apply those functions to it, you'll turn every UV pair into an XY pair. Ideally, that change is done nicely, by which I mean it's one-to-one. You would have a hard time if the region, well, here we're showing S in the UV plane being converted into R in the XY plane. But what if S got like folded up or crumpled or, ran into itself some way down below? That would be bad. So we want super nice transformations. We want a thing that, well, we want this property. A point in the UV plane has exactly one image in the R space, in the XY plane. So every point of S maps to exactly one point of R. That's one-to-oneness. So, do I want to show you this? Yeah, this is actually not a bad picture to look at. If we were doing a polar coordinates transformation, the XY space is what we're used to. You're not used to thinking about the R theta space this way, but sort of unwind R and theta and think of them as rectangular coordinates now. Okay? The whole line along this edge has R equal to 0. And theta is running from 0 all the way to 90 degrees. Okay, what is that? Well, if the radius is 0, you're at the origin. And so all the points along this line get mapped to the origin. Do you see how that's bad? So this example that they're giving us has a real pathology in it, that many points get mapped to 1. All that orange stuff gets mapped to this orange dot. It's not one-to-one. But it's only at that single point that it fails to be one-to-one. As soon as you're a little bit off, even if R is like 1 over a million, you're going to have this, the orange thing shifted over just a little bit would be right next to that. And that, instead of turning into a point, will turn into a tiny little arc. It's okay that it's tiny, as long as it's not width 0. You can have one-to-one mapping there. All right, so the R that shows up in all our calculations of R dr d theta, that comes from how do we change dr d theta stuff into dx dy stuff. Area in the one system turns into area in the other. The way the coordinates work, that changes the area by a factor of r. So I want to see how, wait a minute, I gotta back up and see how we actually do that. Did they show it? I was reading this before and I didn't. Let me show you this thing, and because this is the answer to the question that I'm not doing very well. But it's called the Jacobian determinant. Now, we've seen another matrix determinant used in stuff. Remember the Hessian matrix and its determinant for sort of multi-dimensional version of the second derivative test. But notice this is totally different. Why? Well, first of all, there's two functions involved. The Hessian determinant was for a single function. So we've got a x coordinate that's controlled by this function g of u and v. And then there's a typo right here. That should say y equals h of u and v. That typo is kind of a bad one. Anyway, those are x and y coordinate functions. And the determinant we're making here has all of x's partials with respect to u and then with respect to v across the top row. And in the second row, it's partials of y with respect to u and with respect to v. And when we do our little x, multiplying this way and then subtracting what you get when you multiply like that, this is it. Now, I'm not loving that form of it for, well, one reason is that it's a little awkward to use that Leibniz style notation. Sorry, concentrated on making a change here. So let me say this in a different way. We're taking x and y coordinates on one side and u and v coordinates on the other. And what we were actually looking at is the mappings, what are called the transformations back, the transformation from u and v back to x and y. I usually think of x and y as our sort of home base. Those are the standard coordinates, and u and v are the new guys. But if we're going in the reverse direction, we're going to get x as a function of u and v and y as a function of u and v. That's the pieces that we were just looking at. This transformation has sort of two elements to it. X is equal to some function of u and v. I hope I'm not changing the names, what they say in the book. Yeah, figures. They called it G. So I don't want to change the names. G of u and v, and y is equal to h of u and v. Yeah, so the matrix we get here is first take G's u derivative and G's v derivative. And then take h's u derivative and h's v derivative. Put those guys into a little matrix and take its determinant. So you get overall, do I have enough space to write it in here? You get gu times hv minus gv times hu. Just fit. I did make it tiny to fit it, but it just fit. Okay, so that's the factor by which the area element changes. That's either the r or the rho squared sine phi that we had when we were doing spherical coordinates. Of course, in spherical coordinates, that was three-dimensional, so it would have been x, y, and z are functions of rho, theta, and phi. We have a bigger matrix. Let me give you an example of this that is pretty small, so we can start easy and get worse. If I had an integral where the region of integration was a diamond-shaped thing, it's actually just a square on its side. Right? So that's the origin. This is the point 1, 1. This is the point 2, 0. This one is 1, -1. The four corners of a square, though, aren't they? Each side length is √2, and you can think about the angles are all 90 degrees. Okay, so if I had to integrate over that region, well, I mean, I guess I could go up to there and then just have, I could divide this thing up into 4 bits like that, and I'd get triangular regions now that have limits that are reasonable to do. So see, this line here is the line y equals x, but this line here is what, 2 minus x? The boundaries have changed here. But let me just change how you're looking at this thing. And I literally mean just rotate the view in your head. Go to that. What if we had a new coordinate system that went that way? That would be much better, wouldn't it? In fact, I kind of like to have this all happen in between x or u equals 0 and u equals 1 and v equals 0 and v equals 1. How do we come up with that coordinate system? Well, u is just the sum of x and y. So if we're going back this way, I'm sorry, maybe I should say that differently. No, let's say it that way. If I said u is equal to x plus y, and v is equal to x minus y, you can figure out what x is in terms of u and v. Have you ever done this kind of a solving a little system of equations? I think many people have. The trick on this particular one is if you add both sides together, the y's get canceled. So if we have x plus y plus x minus y, there's no more cancels. You'll end up with 2x on one side, and that would be u plus v, because I just added the two equations together. And so that's easy. It turns x into 1/2 of the sum. Like that. If I subtract these things, these two equations, it'll be u minus v on the left, and x plus y minus x minus y. Well, the x minus x will be gone, and the y minus minus y will make it a 2y. So that one turns into y is equal to 1/2 of u minus v. Okay, those are our functions that give x in terms of u and v and y in terms of u and v. And gee, they're not so bad. What is the Jacobian matrix? I want to take this top guy and take its u derivative. Well, that's 1/2. Then take the top guy and take its v derivative. That is also 1/2. I'm trying to write this Jacobian matrix down here, so let's call it something. And then do the same thing with the bottom row. Y is equal to that. So that's also 1/2 of u. So it gets a plus 1/2 there. When I take it, I'm taking a partial derivative, right, to get there. And then this one, it's -1/2. So when I take that determinant, I get 1/2 times -1/2. That's -1/4. And then I subtract 1/2 times 1/2. That's also 1/4. -1/4 minus is -1/2. There's a little funny business going on here that it came out negative, which is actually just telling me that if I do the area thing in the UV plane, I'm going to get negative area, and when I move it to the XY plane, it'll turn positive. But most of the time, people just say, take the absolute value. You know, area is always a positive number, so don't worry about it. So you can take J to just be the absolute value of that. So it's 1/2. Now, what does that mean? Let me make some pictures here. My diamond shape in the XY plane, I'd mentioned it has a side length of √2, right? XY axes would be here. When I did this change of coordinates, let's watch what happens to some of these points when we change coordinates. What happens to the point right there, which is 1, 1? Wait a minute, maybe before I ask about that one, I should ask about what happens after this transformation to the point 0, 0. Oh, okay. So the origin gets mapped to the origin. I'm coming back to my picture. This is the XY plane. My UV, should probably make V be vertical. My UV plane has the origin. This mapping goes that point right to there. What happens to 1, 1? I add it, add the two coordinates, and I get 2. And then I subtract them, and I get 0. So 1, 1, this leg, and we can do it in a different color. That leg ends up right there. The leg between 0, 0 and 1, 1 becomes the leg between 0, 0 and 2, 0. What about this point? I don't think I have any other colors handy. This might be a blue one. That point has coordinates 2, 0. No, it's black also. I'm unlucky. Anyway, what happens to that? When we add the coordinates, I get 2, and when we subtract the coordinates, I also get 2. It's like here. So that leg became this one. I'm going to put some directions on these things so you see that we were moving around the diamond from here to here to there, and we're moving around a square on this and these axes. Okay, finally, what happens to that point? Because after that, we're just going to go back to 0, 0. That point has coordinates 1 and -1, and I got u by adding these things, so I'll get 0 as my u coordinate, and when I subtract, it's 1 minus -1, it's 2. So in the UV space, my third point is right there. And so that's easy to see that we then return to the origin. Return to the origin there. Now, one thing to notice, and this explains why this number came out negative, is this is a clockwise oriented passage around the square, or around the diamond, and this is a counterclockwise oriented passage. That's why we're getting the area, or the negative sign in the Jacobian determinant. But let's just check that 1/2 is the right feature. Can you figure out what the area of this thing is in the UV plane? Yeah, its width is 2 and its height is 2, it's 4. And what about this guy's area in the XY plane? Well, I worked out its side length was √2, so √2 times √2 is 2. How is area related between UV space and XY space? It's half as big, right? That's why we had that 1/2. Pretty cool. This one is an example where the change of coordinates is called as linear, and that's a very common form of coordinate change, but it doesn't have to be. We can have XY systems that transform into 1/x and x times. You can have all kinds of pairs of things that stay kind of not orthogonal, but at least opposite, not the same directions. That they don't all end up. You don't want the coordinate system to collapse so that the x and y axes or the u and v axes are running in the same direction. But as long as you get a sort of a family of curves for u as a constant and a different family of curves for v as a constant, that'll work. And in various physical problems, that's exactly what we'll do. I guess we should end this by talking briefly about the spherical coordinate system. So. this, there was a thing in the book that does the Jacobian for just polar to rectangular. That's not what I wanted, though. I wanted to see something that's three-dimensional. Oh, okay. And they're getting into all kinds of stuff that's about strategy. In fact, that's funny. I didn't realize they did the same example I was just working with, although kind of, no, it's the same exact one. Uh, why do you make certain changes versus other changes? This is a case that happens often. What we just looked at was an example like this. You can change so that the region becomes rectangular in the new coordinate system. Use the type of shapes that are along the two axes, the boundaries of the region, and turn that into, a change of coordinates. But I was really hoping to find the polar. Well, it's not here. So let me give us the change of coordinates in spherical. Whoops. I gotta shift to the drawing mode. Remember, in spherical, we sort of have the z-axis, but we don't really talk about z. But from the z-axis, we have an angle phi that's measured down from the North Pole to locate a point. And we have a rotation, a radius, but rho, because it's not radial, it's out from the center. We'd like to use a different letter for that. And then that whole thing was happening in a plane, really, determined by the z-axis and this line segment. Well, that plane can be oriented with respect to the x-axis by giving some angle theta. That's how far around we are from it. I'm seeing that the picture in my mind, this is stuff that's happening in the xy plane, and this is happening down from the z-axis, but they both just look like arcs between pairs of lines. We saw this in the cantaloupe. Honeydew. So let me first figure out this, which is the projection of this point whose coordinates are theta, phi, and rho, straight down into the what is that? Phi equals 90 degrees, the equator, equatorial plane. How far is that out from the center? Well, let's just write a squared up version of the triangle that I've been looking at in perspective there. This is a true 90-degree angle. This is r, this is rho. I don't know what this is. It's the z coordinate of that point, but I do know what this angle is. That's phi. So we've got the hypotenuse of a right triangle and the side opposite the angle. R over rho is equal to sine phi, or R equals sine phi times rho. Right. Now that's useful because that's actually our polar coordinates are. We were in spherical coordinates where r is measured out from the origin to a point in space, but it's in the xy plane, its projection, and we've got r and we've got theta, and we know how to get x and y from them. So x is the cosine of theta times r, which is the sine of phi times rho. Similarly, y is the sine of theta times, that's theta, times r, which is sine of phi rho. Finally, z. What's the z coordinate in terms of rho, theta, and phi? We actually did just see that a second ago. I kind of brushed past it, but this height on that triangle, that's z, and that's the adjacent side to phi with a rho as the hypotenuse. So z is rho times the cosine of theta. Excuse me, I just misspoke. That's cosine of phi. So those are our, oops, that's off the screen, sorry. Those are our coordinate transforms back from rho theta phi to x, y, and z. Can we work out what the partials are with respect to theta, phi, and rho? Let me give you the Jacobian matrix here. I can write it. I don't know if I can get this on the, keep the formulas on the screen and write the Jacobian matrix at the same time. Okay, what order were we doing the variables in? I'm going to take it in the same order we're seeing them. Theta, phi, rho. So theta's partial of this, you think of the other things as constants, and cosine turns into minus sine. So we get minus sine theta times sine phi rho. Those constant things, or things that don't depend on theta, just come along. I'm guessing this is not going to fit on my sheet, but I'm going to do my best. The next thing is the phi derivative of that whole mess, the x coordinate, and that is going to be cos theta, because that theta is a constant, cos phi, because phi is the variable, and rho, because rho is a constant. So what did I just say? Cos theta, cos phi, rho. All right, I gotta do some trickery to make the page wider. I'm just gonna move it sideways and write on the next sheet. Yay. What about the rho coordinate, the rho derivative, the rho partial of our x coordinate? That's going to be, rho is just the variable, the other things are constants, they come along, and the rho turns into a 1. So we get cos theta sine phi. Yay. That's just the x coordinate. Now we got to do the y coordinate. It's the same thing though, right across. We're going to take the theta derivative of this and get cos theta. And the other things are constants as far as theta is concerned. So we get sine phi rho. Sorry, that theta almost looks like a B. Fix that. The middle guy, that's the y coordinate function taken derivative with respect to phi. That's going to be sine theta cos phi rho. And then the last guy, that'll be in this row, this will be that guy's derivative with respect to rho, which is just going to be sine theta sine phi. Oops. Finally, one more thing. This is a big old mess, but it's really just a 3x3 tic-tac-toe board with formulas in each slot. For this, we need the partials with respect to theta, phi, and rho of that formula. Now the theta one is not apparent here, right? So this is just a constant if you're only looking at theta changes, and that means it becomes 0. When we take its partial with respect to theta. When we take a partial with respect to phi, it does move, so the cosine becomes minus sine. We end up with minus, can I just do minus rho sine phi in that order? For some reason, I usually like to see my rows out front, and a lot of times I've written rows in the back. And then finally, the rho derivative. Well, that's rho to the first power, and cos phi, that the only thing that survives is cos phi. Right, that's the determinant we need to find, and this is the same calculation you do when you do a cross product. So it's going to be this one times that x, positive of those minus the product of those, then it'll depending on how you do it, it'll be the negative of this one times the wide x, or you could have that one times the x that goes around the side and not have to. But it's all good in the end. It's all going to reduce to rho squared sine phi. So, sorry, because I know this Jacobian determinant is exactly the factor that converts d rho d theta d phi into dx dy dz. And that's what we found previously by thinking about the geometry of it. So this is quite a challenge now. Can you guys work out this determinant? It's a big 3x3 determinant, and I'm claiming it just reduces to that. I'll leave you to that. it's a good challenge, and it's fun algebra actually. Okay, so that's the last we're going to say about that until we see it again in section 17.5, talking about change of coordinates. Where do I want to go next? Back to the browser. Okay, sorry. Find myself here. We're ready to talk a little bit about chapter 17. The first thing in chapter 17 is about vector fields. I'm going to return to looking at some stuff in the book in a sec, but first, if I relearn how to steer this thing, I want to make some drawings. Yeah, we have done functions that have single input and then multiple outputs. That's what space curves were. We have done functions that had multiple inputs and a single output. And z is a function of that, and that's a surface. Now, we can't really visualize it anymore if it has 3 inputs and an output, but it's the hyper version of a surface, and we could still do integrals with that, and we could still work with things like that. While we were playing with space curves, there are several instances we came up, well, in various places we've come up with, we've seen examples of functions that have multiple inputs and multiple outputs. And if the numbers match, that is 3 in and 3 out, these are called vector fields. I suppose it could be that we could have 3 inputs going to 2 outputs, or 2 to 3. But the general case is you want to have the number of inputs and the number of outputs be the same. So you can think of this in an interesting way. So I've just drawn it with 3, but think about 2 for a minute. What this means is at every point in XY space, I get a vector. I get a triple of numbers that come out of it. And that's something that I could draw at that point. So I can make an arrow. But what makes it a field is that we can do that everywhere. We can come over here and have an arrow, and over here and have a different arrow. And these arrows might point all over the place. One trick that people do, because it tends to be the case that you can have things that end up looking like that, where nearby points have arrows that cross each other, and it can get really confusing looking. So what people tend to do is just shrink the arrows down, the ones that are where you're drawing the outputs at a particular input. So we would shrink all of those guys by some scale factor. In other words, make this guy be only a fifth as long, and these guys would be like that and like that. And then if you're used to reading diagrams that have all the output vectors shrunk by a scale factor, it's still pretty legible. And they tend to, if you choose the scale factor right, you avoid things that look overlapping. So yeah, let's transition to looking in the text, and I'll show you what I think is a really nice little app they throw in at us. But there's, oh, great pictures, airflow over a wing. That's a vector field. They're showing a lot there. That's a solid model of a hurricane weather system. And what's down there in the XY plane is the surface winds. And that's a vector field. You know, the winds around of a hurricane or any cyclonic storm converge in towards the center. They suck you in. It's one reason to avoid them. Well, they're showing magnetic fields. That's a vector field. We've seen a bunch of those. I wanted to show you this app they have in here. Oh, well, maybe first we ought to stop and look at the definition. A vector field in R2 is a function f that assigns to each point in the region a vector whose one is a function f, the x-coordinate of that vector is a f of xy, and the y-coordinate is g of xy. By the way, that's actually the same thing we were looking at in the last section in chapter 16. A change of coordinates is also can be thought of as a vector field. It's two inputs and two outputs. Right. So they're going to start giving us some examples. Now look at this one. Capital F of x and y is the vector 2x, 2y. Or you can write it in the ij unit vector style. What does that do? Well, at every point xy, you get a vector that's twice as long as the corresponding position vector. This is why you would want to scale things. And here's a mapping of that. Oops. Yeah, so what's going on here is I can move this plot point P. It turns out you just click anywhere else new and it gives you a new P. You see the position vector for P would be, here it's about 2/3, I guess. The vector we plot at that position is twice as long as that position. So if I go somewhere more up towards the y-axis, the vectors get longer and more straight up. If I'm back here, I'll get negative direction. So that's good. If you play around with a bunch of different positions for the P, the input, and see what the vector that's drawn there, the output vector is. But rather than that, there's this thing you can click on and get it to draw them all at once. And this is where they have used the thing that I was talking about. They've scaled all of them down a little bit. I can actually put the two of them on here together. See, this P is pretty long, so long that it goes off the screen, whereas it's still off the screen. There we go. Now it's on the screen. The vector that they've actually drawn here is about 1/10 as long as that one is, right? So you just have, that's a thing to just get used to. The output vectors are going to be drawn scaled way down. That kind of field is actually pretty common. You know, things that start out at the origin and start moving faster and faster and faster away from the origin. We live in a universe that's like that. You're looking at essentially a picture of the Hubble shift, right? Galaxies are moving away from us based on how far away they are. So these would be the velocity vectors of galaxies receding away from us. We're going to look at these three things, which are all of them interesting special cases. This first one is called a shear vector field, and what is going on? The x-coordinate of things is 0, so the output vectors are going to either go straight up or straight down. They won't go side to side at all. And the y-coordinate of the output depends on what the x is. So when I'm here with an x-coordinate of like 2, the y-coordinate of this vector is 2. It's going 2 units straight up. When I'm at x-coordinate of 0, it's 0. And the thing has a hard time drawing a vector of length 0, so it does that. But when I'm like there, I get a vector that points downward. So upward there, 0 when you're in the middle, downward over there. Let's look at the field. This is an interesting vector field. A lot of times wind does this. You'll have two bodies of air moving past one another, and you'll get this effect in the middle. This is where cyclonic storms come from. In particular, tornadoes can be generated when you've got rapidly moving air going past other rapidly moving air, and they're passing each other in opposite directions. It starts spinning around there. Yeah, that's called a shear field. I guess it's sort of like scissors. If you were caught in the middle, half of you would be being pulled in one direction and half of you'd be pulled in the other direction. So yeah, that's a shear field. How about if we wanted to make a shear field that went the other way? That is, up here we'd have vectors going in the positive direction, and down below vectors going in the negative direction. I'm going to come back to that question, but we can just figure out how to do that. There is another example here called a channel flow, and it's only going to draw stuff between -1 and 1. Okay, what it has done is use the y coordinate to determine what the x coordinate is, and you see this is some sort of quadratic. So the y coordinate, sorry, the x coordinate of our outputs is quadratically dependent on where we are vertically. Let's try moving up to a point closer to the line y equals 1. Okay, it's getting really tiny. Does it make sense that the vector gets tiny when y is close to 1? Yeah. The y coordinate of that vector is always 0, so these things always point sideways. And the x coordinate is smallest when you're near -1 or +1, and it's largest when you're right on the x-axis. Right? So when I throw on all of the vectors, and you see it, this is actually really really the way flows in the channel work. I think it tends to not be quadratic like this, but still in the middle of the channel you'll have nice big vectors. The flow will be strong. When you get closer to the edges of the channel, like you think about this as water flowing in a pipe, there's drag, and so the water over near the boundaries gets slowed down. There's a common use of this in medicine where they want to give a diagnostic about how healthy someone's arterial system is. And it's to figure out the ratio of the fast-moving stuff in the middle to the slow-moving stuff at the edge. If your arterial walls are full of plaques and grossness, then this friction is higher, and you'll have very slow-moving blood flowing along the outer layers of your arteries, and yeah, can be a problem. So that's a cool kind of vector field. And the last one we're looking at is called a rotation field. I just want you to notice what has happened between the x and y inputs and the x and y outputs. The x coordinate of the output is the y coordinate of the input with a minus sign on it, and the y coordinate of the output is the x coordinate of the input, so it's switched the roles and made one of them minus. Now that's kind of hard to play with. We could move around at various points and start getting the sense that this does lead us around in a circle, doesn't it? It becomes much more obvious when you turn it so that you're seeing all the vectors at once. Admittedly, they're all shrunk down a little bit, but you see that's a rotation, right? You've got a flow that's going around in circles. The last thing I want to do in this section is show you something I did in Desmos. This is the 2D Desmos, right? So I made up this sheet a while ago, but it was after I started playing with the 3D thing, and it has that vector command, which it does not have in ordinary 2D Desmos. So I decided to make my own. This is a roll your own vector command in Desmos 2D. They have a funny convention that people use when they're programming in Desmos, which is you have the names of things by using subscripts. So I think it needs to have only one letter as the main name of a thing, but you can have whatever you want as subscripts, which means you can do stuff like what I've done here. You type v subscript ector, and that's going to be a function. I'm defining a function. In fact, what I'm defining is a function that just draws a little polygon. This is a function of two things, and those two things will be two-dimensional points, A and P. I don't know why I chose those particular letters, but that's what I did. Let me just show you what that polygon that it's drawing is for a second. You've got a point A and a point P in the plane. What it's going to do is draw from A out to P. Then it is going to work out a little bit on either side of that 2 points. And so it's going to go out to there, over to this one, back to here, and close up by coming back to A. So it's a funny polygon, but this passage of going through those 3 points and A creates something that looks like a line with an arrow on it, which you can definitely see in my graph that's right here. In fact, isn't that my shear graph that we were just talking about? Instead of the shear happening side to side, this is shear happening vertically. What was the formula for this? Oh, yeah, I do want to point out one thing that I would love to make an improvement to this vector function I've created, but you can probably see, especially if I zoom in on something, sometimes that's A right there, and that's P, and the arrowhead I've got drawn is bigger than the line segment between the two things. So when you end up having these arrowheads that are just heads and there's no stick sticking out of them, that's what's going on. You've just got a very small vector. I've been trying to think for a while about how to shrink the heads when you get to a smaller size, but I don't want them to grow without bound when you're at larger sizes. So a little tricky thing to do. Okay, so I want you to just ignore the next few cells in this Desmos window. Gotta double check that I'm showing you the right window. I am good. The last thing we're going to do is called a list comprehension. I've done this in front of you a few times, but what is it? It creates a big list which contains lists. So for I from -3 to -2.75, all the way up to 3, that's going from -3 to +3 in increments of a quarter, 0.25, right? And same thing in the J direction. So we've got I and J running through those values. That's a total of 625 elements, because apparently I have 25 values in each of I and J. We're going to draw the vector that goes from ij to f of ij, and f was defined right there. It's got a 0 x-coordinate, it's got a y-coordinate equal to the x-coordinate of the input, and we're dividing by 5 to make it a little bit smaller so that we can see things well. So that's our shear. Now, how about a rotation? I'm going to just change the F here to make a nice rotation. Remember what they did before? They made I think it was the x-coordinate was the minus of the y-coordinate. I'm going to make the other choice. The x-coordinate will be the y-coordinate, and the y-coordinate will be the negative of the x-coordinate. You see that's a rotation field too, but it's going around the other way. I just wanted to show that you can get rotations in either direction. Well, maybe that's obvious. Okay. There's lots of other fields you can build, so I don't know quite how to do this. Maybe if I hit the share button. I was hoping it would show a QR code, but it doesn't. And I don't think you can see the whole URL on that screen. I will try to to send you guys this in a message. But that'll get you the 2D vector field drawing capacity in Desmos, and then you can adjust your F to play around with various other vector fields. And I guess, oh, I just said F, but make it clear that was capital F, the thing that was a function of two input variables and gave you two output variables. Yeah, all right, so I think that's where we need to get to for today. I'll come back with another video for 17.2 sometime tomorrow. Adios.